In this chapter, or in this section of lectures, we're going to talk about the electronics of transition metals. And so this will really go back to when we learned about the electronic structure of the atom and how our electrons are arranged relative to the nucleus and in what types of orbitals. So let's start with a little bit of a review and definition setting. So, building off our last chapter about representative elements, let's start with a definition of transition metals. So, these are going to be elements that have partially filled d orbitals. Uh, and so that's really going to be our rows that include groups 3 through 11. Group 12 is a little bit different. It is right here on our transition metals. And we've talked about how the group 12 elements really behave a lot more like our alkaline earth metals right here, because they have a filled set of d orbitals. And so they don't behave in quite the same way as transition metals. At the same time, I'm also going to tell you that we sometimes consider them transition metals because they sometimes share the same properties, and so are included in the same group. Uh, and so, which is to say, group 12 kind of behaves in a couple different ways, similar to the metalloids taking on properties of two different groups, metals and nonmetals. Group 12 is a transition metal, but also acts more like an alkaline earth metal, and so it kind of bridges between those two groups. We also have then our inner transition metals, and these are the lanthanide and actinide series that are really a subset. They're located right here in the periodic table. And so we're not discussing those in this chapter. We're going to focus just on the transition metals rather than the inner transition metals. And within our transition metals, our first row of transition metals that have electrons occupying the 3d orbitals, so our first period of transition metals, is our most reactive of them all. And this table has just kind of like all of the little pieces of information about each one in one spot for your reference. This isn't something to go over with a fine-tooth comb and memorize. But it's showing atomic number and electron configuration and radius for each of these. As you can see, it gets smaller for the most part as we go across the periodic table, but not by much. And our group 12 element, again, kind of doesn't fit that same pattern. Zinc kind of stands out as having a large increase in size compared to a decrease in size like you would expect. One of the things that's really interesting about this table that I'd like to draw attention to is the common oxidation states. Now, these aren't all of the oxidation states for each of these elements, just the ones that we're most likely to see. And for many of these, they have more oxidation states available to them. But I think it really highlights how, again, versatile these metals are. And so for many of these, you can see they have at least 2 common oxidation states, some of which have more, like vanadium has 4 common ones, and so does manganese. I'll also say things like iron have been shown to, while the most common ones are +2 and +3, there's lots of evidence of nature utilizing iron as a +1, a +4, and a +5 ion as well. And so these oxidation states are kind of a base, what we most commonly see, but there's more possibilities. And that's in a real contrast to our other elements in the representative groups, which are typically just the one oxidation state, or for our post-transition metals, maybe 2 different oxidation states are possible. So in talking about the electronic structure of transition metals, let's do a brief overview of electron configurations, which were covered in Chemistry 161. So here's my periodic table broken out by the different types of orbitals that are characterized by the last electron placed in that element. So we have our s orbitals and our p orbitals, d and f. And so we can think of the transition metals as actually being the d block elements, right? Because the characteristic last electron placed within that element is going to be a d electron, and they'll have partially filled d orbitals. Whereas p block elements are likely to have partially filled p orbitals, s block partially filled s orbitals, f block partially filled f orbitals. And so we'll be focusing on these ones. And it's worth reminding ourselves of um, how these orbitals are filled with electrons as we add more and more and more. And so up here at the top, we have our generic electron configuration that'll apply for any element. And it's really showing the order in which electrons fill in an element. And we have then a orbital drawing or diagram right here that shows this relative in energy. And so we're going to always add electrons into an element starting at the lowest possible energy and working our way up. And so that's starting at the 1s level, and then 2s, 2p, 3s, 3p, and then in that third shell of electrons, we start introducing the d orbitals. And they do this really interesting thing where our d orbitals right here, so here are our first d's, they're 3d, they actually come at a higher energy than the s orbitals of the next shell of electrons, the next valence shell. And so we'll always fill first our 3s, then our 3p, then our 4s, and then our 3d before returning back to our 4p electrons within this. And so our 3d electrons are high enough in energy that we actually create a new valence shell of electrons first with those s electrons before starting to fill our d electrons. And so when we do fill them, they're filling in at a core shell rather than a valence shell. And so when we ionize our metal atom, that's a transition metal, we typically lose those valence electrons first before losing the d electrons. So let's review electron configurations with a couple of examples. I've got tungsten and chromium here to walk through. If you have a periodic table handy, you can take a look at it and find tungsten on your periodic table. You're going to find it in the 6th period, so it's in the 6th row. And so we can write out the long version of our electron configuration. We can also abbreviate it by going to the closest smaller noble gas and saying, we're going to use that electron configuration. And for tungsten, the closest one is xenon. So we can say, you know, we're going to abbreviate. Take that electron configuration for xenon, and now we're just going to tack onto it. And when we do, we come down to that 6th row. Xenon is the noble gas of the 5th row. And we start with our s electrons first, because those are going to be lower in energy than our d electrons. And so we're going to have 2 electrons in our s orbital for xenon. And then it looks like we go right into the transition metals, but we have our inner transition metals, our lanthanide and actinide, that are at the bottom of our periodic table that are really a subset. And so our periodic table that we're used to seeing looks something like this, but with our lanthanide and actinides kind of sitting here on the bottom. But these are really inserted right here in between our s block and d block electrons. And so it's really more something along the lines of, let's get hydrogen in there. And then here, so here's our s block, then our f block, then our d block, and then our p block of elements. There we go. And so xenon is in a row that includes the lanthanide series. And so those electrons will be populated first before our d electrons. So we'll go into the 4f electrons and they'll be filled. There's 14 electrons that can sit in 7 different orbitals. And then we come to our d electrons. So we'll be at the 5d. And then looking at tungsten, we have 3 electrons to fill in. It's our 3rd element into our transition metals of that row. So, and then remember the xenon, you would start out at 1s2, 2s2, 2p6, then you'd go down to 3s2, 3p6, 4s2, 3d10, and then we'll go to 4p6, then 5s2, and then we'll do 4d10, 5p6, and then that's where xenon is. That's that 6th one. And so when we when we abbreviate with xenon, we're really saying all of this comes first, which is a fair amount. All right, now let's look at chromium. This is in our first row of transition metals. And so I'm going to abbreviate again, and the closest noble gas is argon. That is smaller. So I'm going to say, let's assume argon's electron configuration and show the variation from that for chromium. And so it'll have its 4s electrons filled, 4s2. And then we have 4d electrons, so 3d4, within our, just looking at its location on the periodic table. And then this raises an interesting point, which is that, and this is something we've talked about before, it's worth reviewing in 161, that a number of our transition metals show not the expected behavior for filling electrons in the order that we described. And what we see is that when we have an element that is very close to having a completely filled or half-filled set of d orbitals, it will actually promote one of our s electrons into that d orbital. And so the reason this happens, so here's 4s, and here's 3d, is that energy difference between these two sets of orbitals is really small. And so if we have our chromium looking like this, where we've got two paired electrons in our 4s orbital, and we have then 4 in our 3d, we will stabilize these d orbitals if we can fill them halfway. And so it's actually energetically favorable to have our d electrons half filled and then have our s electron with only one, or s orbital have only one electron in it. And so whenever we are just one away from our fifth or our half-filled orbitals or our full orbitals, it's very likely that we'll see this kind of exception to how we do electron configurations. All right, in the next video, we're going to walk through how to do the electron configurations and orbital diagram for these elements, nickel, copper, and technetium +2 cation. So try this first on your own, and then you can review the video that follows.